And now we're going. Pause it. All right, so question the first. This is the graph of y equals 1 over x. It's familiar. We've got a vertical asymptote here at x equals 0, horizontal asymptote at y equals 0. What about y equals x over x? So a lot of groups I saw had drawn this line at y equals 1, but there is one value that is undefined here at x equals 0. This also. So the question is, why is 0 over 0 undefined? Let's think about it this way. A divided by B equals C. Okay, let's imagine that form. So that should be the same as A equals B times C. So now let's plug in 0 for A and 0 for B. So if we have A and B are both 0, we've got 0 over 0 equals some number C, and we're trying to figure out what is C. So let's look at this algebraically equivalent thing. If A is 0 and B is 0, we have 0 equals 0 times C. So what's C? C could really be anything at all. And that's why the value C is undefined. It's because 0 divided by 0 doesn't produce a single value for C that makes that algebraically true. And so that's what it means to be undefined. It means like we just haven't defined what that is. So the way that you would write that is a do you know like the proper math term for a hole in the graph? It starts with an R. Alice? Oh, okay. It is removable discontinuity. It's nice sometimes to know the professional vocab. So removable discontinuity. All right. So that's neither here nor there. The real question that we want to answer is, like, why do vertical asymptotes happen sometimes? And the reason I contrasted this, I thought about asking you y equals 1 over x, why does it have a vertical asymptote at 0? And I expected you to say, oh, whenever you have a 0 in the denominator, that's what makes the asymptote. But here you notice we also have a 0 in the denominator, no asymptote. So the question is, how come this case there's an asymptote, this case there's no asymptote? So if we looked at these two graphs, but just at x equals 0, they would look exactly the same. They would look like nothing because at x equals 0, they're both undefined. So the difference between a hole and a vertical asymptote doesn't have anything to do with what's happening at x equals 0. At x equals 0, they're the same. It has to do with what happens as you get really, really close to x equals 0. So here, if you imagine a value that's like very, very close to x equals 0, let's imagine x equals 0.0001. You got 0.0001 divided by 0.0001, which is just 1. So it doesn't, for this one, it doesn't matter how close you get, the value is still 1 until suddenly it's undefined. Over here, let's imagine what happened. Let's imagine x and 1 over x. So x is 1/10. What is 1 over x? 10. Right, it's 10, because 1 divided by 1 over 10, you multiply by the reciprocal, so now it's 10. Let's get even closer. 1/100th is even closer to the axis. What is 1 over x? 100. Even closer. 1 over 1,000 is 1,000. Yeah. So yeah, thank you for playing along. So it's like the closer I get to x equals 0, the larger the y value gets, which is what's forcing that vertical asymptote there. All right, so the mystery function here is tan theta. You do know what tan theta is, right? What's that? All right, so let's write it down just because, notes. All right, so tan theta, sine over cosine. Were you told about this one last year? Okay, so this one is called cotangent. If you want to write the word cotangent underneath so you remember how to say it out loud. There's two ways to define cotangent. Cotangent is the reciprocal of tangent. Being the reciprocal of tangent, like imagine that we'd plugged in sine over cosine here. If you have 1 divided by sine over cosine, and you multiply by the reciprocal, you end up with cosine over sine. And depending on the problem, sometimes it's more useful to think about it this way. Sometimes it's more useful to think about it that way. You know, as will be revealed in due course of time. This one is called secant, or like secant. Not so much secant, but like secant.
I can't see.
Yeah. And secant is the reciprocal of cosine. Shh. This one is called, do you have a guess? Yeah. Cosecant. Yeah, right. You can abbreviate it as XK. Wait, well, this silliness has messed me up. Okay, so is the reciprocal of 1 over sine. Having just said XK, I tried to write XK.
The reciprocal of 1 over sine.
What?
You said the reciprocal of 1 over sine.
Oh, sorry. Cosecant is the reciprocal of 1 over... Wait. Cosecant... Cosecant is 1 over sine. There we go. Yeah, we'll, you know, we'll edit the video in post-production.
Who came up with that?
Okay, we're back. After protracted discussion, we've decided that you just need to come up with a trick that works for you for remembering what these are. Okay, let's think at the bottom here conceptually about inverse trig functions. I have an observation about the test. Let me pause this second. Okay, we're back. You know, we all know about inverse cosine. Like, we've thought about it so far as how do you undo regular cosine? Like in an equation. If you want to, like, if you have something inside cosine that you want to get out of there, you need to undo the cosine function to isolate the thing on the inside. I just want to point out that you can make sense of the meaning of this thing on the unit circle. And let's think about it in reference to regular cosine. So regular cosine, I think you know this, 12.3. What kind of thing is 12.3? What does it represent?
Angle.
Oh yeah, angle. So then cosine 12.3, we have two ways of thinking about it. One way of thinking about it is it represents, right, it represents x over h, that ratio. Another way of thinking about it is it represents the x coordinate on the unit circle. Because on the unit circle, h is just 1. So, I mean, really, it's just that same thing. Okay, so now, inverse cosine. Remember, what do we know about inverses? I guess a lot, yeah?
Like, give it the ratio, I'd say. Like, give it, you put in the ratio, you get the angle.
Right, because you're thinking inverses, it's like the backwards function. It's like the reverse function. So here, the input is an angle, the output is a ratio. Here, the input, 0.3, must be a ratio, or it could be like an x value on the unit circle. And the output must be an angle, whatever angle makes that true. And so I think this fact is going to play a role later on. And I just want you, like when you look at this picture, I don't want you to look at that and be like, I'm going to bust out the calculator. Or like look at that and be like, Meh. I want you to look at it and think, oh, that's a point. Like that input is a point on the unit circle. It's an x-coordinate. And the output is just an angle. And if you think about it that way, it's like, you know, warm and friendly, which is how we want math to be.